Let's talk about acids and bases now. You've had a little bit of introduction in GenChem 1, but we are going to get into a little bit more in depth. So just a little review about what you might know from GenChem 1 is acids and bases, some of the properties of acids and bases. So the taste of acids is sour. Bases are usually going to be bitter. And think about fruit juices if you want to for acids like grapefruit juice, orange juice. They're a little bit sour, whereas bases, and I hate to give you this example, but you might have tasted soap in some time in your life, and that's kind of bitter. The sense of touch. So acids don't really have any kind of specific touch feeling, but bases do feel slippery when you touch them. Again, a good example is soap. Reaction type is for acids is called corrosive, and for bases is called caustic. Now both of these are going to cause burns. There is an acid burn, there's a basic burn. So both of these substances cause burns. It's just that they're different, and it's good to know which one it is so that if you need to get treated or if you need to treat anyone, then you know which kind of burn you're dealing with. So corrosive and caustic, okay, just different kinds of burns. The pH, which we will talk a little bit more about in this chapter, you may or may not have known about pH before, as acids have a pH from 0 to 7, bases have higher than 7 and up to 14. The pH scale ranges from 0 to 14. So lower pH is for acids and a higher one is for bases. Chemically speaking, acids will have protons and bases will have hydroxides. We're going to change that theory a little bit, but in general, if you wanted to recognize acids and bases, this is how you would do it. And then there's the litmus paper test. Okay, if you have a blue litmus paper, it will go red with acids, and if you have a red one, it will go blue with bases. Examples of some of the acids. Now there are two kinds of acids. There are inorganic acid, which we also call mineral acids, and they're organic acids. So there are two kinds of acids we talk about. Inorganic acids or mineral acids are considered to be usually strong acids, and you've encountered these before in your lab and you will continue to do so. So for example, hydrochloric acid, sulfuric acid, nitric acid, phosphoric acid. These are all very common acids that you find in the lab. Common bases that you will find in the lab would be sodium hydroxide, potassium hydroxide, calcium hydroxide, ammonium hydroxides. Those are also all bases. All have hydroxides in them. Again, that's what we said. You know, it's kind of a key identifier for a base. Organic acids are usually considered to be weaker than the mineral acids. Although there are some organic acids which are as strong as mineral, but we'll not get there yet. So generally we'll say that these are going to be weaker acids than mineral acids. So this acid is the most common one that you will encounter. It's called acetic acid. It's written a little bit differently in your GenChem books. It's written as C2 or it's written as HC2H3O2. And I like to write it this way because as an organic chemist, I prefer to write it this way. This is the hydrogen you're looking for. Generally for mineral acids, you will see that the hydrogen is written in the front, and that is what they try to do with acetic acid. Okay, but I generally end up telling everyone that, you know, here is that acidic hydrogen, the proton that you're looking for. The bases are going to be a little bit different. They're usually nitrogen-based compounds. Ammonium hydroxide, all right, any derivative of ammonia, which will be an organic base. So here also this is NH3 would be ammonia, but I replace one of the hydrogens with a carbon, and so this becomes an organic base now. So this is how we get organic bases, and these are also going to be weak bases. Okay, so they're not strong. So anyhow, that's a little bit properties of acids and bases. Now for the definitions of acids and bases, you may know some, you may not know some here, so here's a refresher. For the Arrhenius definition, this was the first definition that came around for acids and bases. Acids are simply proton donors, H+ donors, and bases are going to be hydroxide donors. Okay, very simple, straightforward. And so an example would be HCl for a proton donor, and again, that's why I said you're looking for that hydrogen there. And then bases would be hydroxide donors, so you're looking for OHs. But that was changed later on by Bronsted and Lowry. And so the new definition came out to be that acids are still proton donors, no doubt. They still give protons. But now they changed the definition of bases to become proton acceptors, because it turns out that ammonia is actually a good base, but there was no hydroxide in it. And so you could not really classify that as Arrhenius base. And so it just turns out that ammonia, being a good base, is just a proton acceptor. So bases became then proton acceptors. And that's the Bronsted-Lowry definition, and that is the most accepted definition of acids and bases. The Lewis definition of acid base has to do with electrons. And as you know, electrons are like the best way to define anything, because nothing can go wrong with that. It's an absolute. So for acids, acids are electron pair acceptors, whereas bases will be electron pair donors. So you're looking for compounds which are able to accept electrons. For example, BF3, boron trifluoride, it's in group 3. And that's boron, that's in group 3. And you learned it back in GenChem1 that boron actually has an incomplete valence shell. And even now, if you look at it, boron has only 3 electrons and it's bonded with 3 fluorines, which means it has a total of 6 electrons. So if it has 6 valence electrons after bonding, it has capability of taking one more pair of electron. Okay, so it becomes a good pair acceptor. On the other hand, the electron pair donors, which are the bases, will be anything that have lone pair of electrons, like nitrogen, oxygen, chlorine, anything that has capability of giving an electron. Other examples of electron pair acceptors would be ions, like Fe2+, zinc 2+, because if you have positives, it means that they're capable of accepting electrons. So when you look at the Lewis definition of an acid or a base, you will not see something like a proton donor anywhere. Okay, it's possible. And so that's why the Lewis definition looks, the Lewis acid bases look a little bit different than what your traditional acids and bases would look like. The other thing to remember before we go on is that when we have acids, we deal with hydronium ion and not H+. So we write as proton because yes, HCl is giving H+, but the thing is that HCl as a gas is not an acid. However, HCl in water is considered to be an acid, and you can do a pH test and see this. So HCl gas is not acidic. HCl aqueous is now acidic. So what happens then is that the H+ that comes out of the HCl will quickly bond with water to give H3O+, all right? And so this is the hydronium ion. It's a polyatomic ion, and this is what you would find in acids and not really H+, okay? And again, because they are a solution in water, this has nothing to do with the bases. Hydroxides can exist as hydroxides, no problems. So it's only about acids, okay, that they exist and is a hydronium ion and not H+. What will happen for us in class and in textbooks also, you will see that they are used interchangeably. When you're trying to balance an equation, you will use H+. When you're just trying to write an equation, you might use H3O+. So it depends what you're trying to do, okay? But I just need you to understand that H+ exists as H3O+ in reality, okay, in acid solutions. And then what the other substance that you should know about is the amphoteric substance, which is both acidic and basic in property. So water, for example, is the best case, okay, for an amphoteric substance. So water can behave like an acid as well as a base, okay. The acid-base reactions are very typical, and I know you've written some of these before. Most of the reactions that you might have written would be for the Arrhenius acid and base, which means that the acids are going to be the proton donors, whereas the bases would have the hydroxides in them. So typically what you would see is that acid plus base gives you salt and water. So the only way you can get water is if you had hydrogen in one case and hydroxide in the other. So which means the acid is giving the hydrogen, whereas the base is giving the OH. So HOH makes water. So this is true only if you have an Arrhenius acid and base. You cannot have it in any other instance. And so this equation will hold true for Arrhenius acid base. But typically you will have most bases that have hydroxides in them. So acid plus base gives you salt and water. So whatever the ions are remaining, then that will give you the salt. So the Bronsted-Lowry acid bases are slightly different because here the acid can still be the proton donor, but the base is not required to have a hydroxide. So in this case, it's just a proton acceptor. So in this case, what happens is these two will just combine to give you a salt. There is no water, okay, in this case, because there was no hydroxide. One of the things about an acid-base reaction is that why do acid-base reactions even take place? Why do they happen? Okay, I mean, do all acid-base reactions give you products? Is it always going to be like this? Well, most times, yes, and it depends essentially on the strength of the acid and base, which is really part of our topic for this section, is that if you have strong acid and base, the driving force is to go towards product that will be weaker acid and base. Okay, so anything strong is going to start reacting to give something that is a weaker acid-base combination. So that's the driving force for any kind of an acid-base reaction. So sometimes if you have very weak acid or base, they will actually not react at all. So it does happen, okay, that you will not get reactions in some cases. So, but for most part, you will see something because obviously you do want reaction to happen. There are three kinds of acids that you should understand, and they're called monoprotic, diprotic, and triprotic. Monoprotic acids will give only one proton on ionization. Now remember, when you have HCl in solution, like HCl as an aqueous solution, you have hydronium ion, which is the H3O plus and the Cl minus. Okay, so the H is coming from the acid and going to attach with the water, H2O, okay? So that's what we are talking about. How many protons are given off by the acid? That's a monoprotic acid. So the monoprotic acid will give one proton, so like HCl, HNO3. A diprotic acid will give two protons then on ionization, which means that you will get two hydronium ions in the process. So example would be H2SO4, okay? And so the H2SO4, you generally end up writing two steps for this, okay? When you're in GenChem 1 or when you're just learning about acids and bases, we don't write two equations. We just say, well, you have two protons, and so when you start balancing equations, you use mole ratio of 1:2, okay? But things are going to be slightly different now because we have to learn a little bit more about what happens to this diprotic acid. In the case of diprotic acid like H2SO4, the first ionization is very nice. Okay, so for example, H2SO4 plus H2O gives you the HSO4 minus ion, which is a hydrogen sulfate ion. So it gives you this ion and then H3O plus, the hydronium ion. That is totally expected. The second ionization, which is supposed to happen from the hydrogen sulfate ion, is actually in equilibrium, okay, which means that it is not a complete reaction to give you sulfate ion and the hydronium ion. So the first reaction goes to completion, no problem. The first proton will ionize, no problem. But the second proton does not ionize very easily, okay? And this has a little bit to do with the charge that is already on the sulfate over here. The hydrogen sulfate has a negative charge, so it does not like accommodating two negative charges, so it prefers only to do one ionization. So the second one is a little bit harder to do, which means that the acidity of H2SO4 comes primarily from the first ionization. The second ionization contributes very little to the acidity. Okay, and so we'll have some calculations and you will see how that changes the pH of the acid. Okay, so anyhow, this is what happens when you have a diprotic acid. In a triprotic acid like phosphoric acid H3PO4, now you have three ionizations going on. The first one, just like in H2SO4, and then the second one, which would take it from dihydrogen phosphate ion to hydrogen phosphate ion, and then hydrogen phosphate ion to just phosphate ion. So the first ionization again is not going to be a problem. The second one is going to be slightly a problem, and then the third one will be even harder to do. Okay, and so triprotic acids generally do not really mean that you have three hydrogen ions in solution. It just means that you have three ionizable protons. How much they are ionized is a whole different thing. Conjugate acids and bases are formed as a result of acid-base reaction. So what happens is that when you have an acid-base reaction going on, then there is of course the gain and loss of a proton. Okay, so the gain and loss of a proton will lead to what we call a conjugate acid-base pair. So the conjugate base occurs from an acid, it forms from an acid after the donation of a proton, whereas the conjugate acid forms when you have a protonated species, which makes sense because the base is going to accept a proton, so suddenly it looks like an acid. Whereas the acid has given away the proton, so it starts looking like a base. All right. So here is an example of a reaction where you can see this. So for example, you have HCl and H2O, just a simple ionization reaction. So hydrochloric acid, which is the acid, it loses a proton to give hydronium ion, and it will also give Cl minus ion. So the acid over here will give Cl minus the chloride, which is now called the conjugate base. All right. The water, which was the base in this reaction, because obviously hydrochloric acid is the acid, so water is the base. Water then ends up gaining a proton. So if it gains a proton, suddenly it starts looking like an acid, which we know hydronium ion is an acid. So this conjugate acid then is going to be on the right hand side, and it is formed as a product. So acid-base reactions will give you conjugate acid and conjugate bases. Okay, so when I was talking to you about before how these reactions progress and why an acid-base reaction happens, well, these acid-base reactions are supposed to give weaker conjugate acid and weaker conjugate bases as a result. And so once this is formed, this reaction should not be able to go back, okay, in some cases. So right now it shows that it is going back, but generally it will not go back. So in case of a base, what you would have is the base will gain a proton. So now water here is acting as an acid, okay, is behaving as an acid, and water here was a base, remember that, okay, and water is an amphoteric substance. So depending on what it is reacting with, it can change its behavior. So water here is an acid, which means if it is an acid, it is going to be a proton donor. So if it is a proton donor, then it loses a proton, which means that it becomes a conjugate base. The base, on the other hand, will accept a proton. So once it accepts a proton, it becomes a conjugate acid, the NH4+. So generally, the way to identify conjugate acids and bases on the right-hand side is see if you have an extra hydrogen on it, okay? Generally, your acids are going to be positives and your bases are going to be negatives. And I will not say that for surety because, of course, you have the diprotic and the triprotic acids. So it's not always going to be the case. You have to see which one has the more number of protons. The more number of protons means that you have an acid. The less number of protons mean you have a conjugate base. Okay, that's how it works. Here's a little bit of a list of conjugate acids and bases. So for example, acetic acid will give you CH3COO minus. So this is again minus the hydrogen over here. So conjugate bases are going to be negative. Water's conjugate base is hydroxide. Ammonia's conjugate base, all you have to do is remove a proton. So just remove a proton. So when you remove H plus, that means you're creating a negative charge. Okay, so H2SO4, the conjugate base is going to be HSO4 minus, the hydrogen sulfate ion. In case of the bases where they form conjugate acids, now you have to add a proton. So when you add a proton, you just add H plus to it. When you add H plus, you have to add the hydrogen and you also have to add the plus charge, okay, to it. So ammonia, for example, gives ammonium ion. Water, when you add hydrogen to that, it will give you hydronium ion. OH minus, the hydroxide, which was a conjugate base over here, if you add H plus to that, it will obviously give you just simply water. And then here's urea. Again, this is an organic acid, organic base. You add H plus to that to give the conjugate acid, and you can add the hydrogen here or here. It doesn't matter because both of these are nitrogens here. So we added it here, and so this gives you an H3 plus. So these are the conjugate acids and bases that are formed as a result of reaction, and they will always form. There's nothing like you can do. It's just a matter of classifying these ions that are formed into some sort of a name. So when we talk about them, we know what we're talking about. So the conjugate acid-base strength, now remember this is an important part because this is what the driving force of a reaction is. Any acid-base reaction will lead to a weaker conjugate acid-base product, because if it is not weaker, then you don't get reaction. Okay, so you cannot get stronger acid base as product. You have to get the weaker acid base as product. So which means you have to understand about the strength of the conjugate acid and base. So here is the general theory. Okay, if you have a strong acid, it will give you a weak conjugate base. If you have a weak acid, it will give you strong conjugate base. And the same thing happens with the bases. Strong bases will give you weak conjugate acid. Weak bases will give you strong conjugate acid. Once you know what your strong acids and your weak acids are, then you can predict reactions, okay, and see if something is going to happen or not. Because once you know strong acid, you know it's going to form a conjugate base. So this reaction is happening. A weak acid will give a strong conjugate base. Obviously, this reaction is not going to happen because you can't have stronger acids and bases as products. Okay, so that's where this becomes really useful. So for example here, when we have these kind of reactions going on where we have what sulfuric acid, this is just an example of what's going on. You have a strong acid. As far as sulfuric acid is concerned, is one of the strongest acids that we have. So sulfuric acid will ionize to give HSO4, which is a weak conjugate base. Okay, so weak conjugate base, and it's also a weak acid. The weak conjugate base here can give one more proton. Okay, and so this one gives you the sulfate ion. So the sulfate ionizes even the weaker conjugate base, okay? And so this is what the driving force is. Once you're going towards the weaker and weaker, it's going to try and go there at that point, which is why if you have sulfuric acid in solution, you will not find any H2SO4 in the solution. You will find either hydrogen sulfate ions or you will find sulfate ions, okay, along with the hydronium ions. You will never find sulfuric acid ion as a molecule by itself, because everything will ionize to give the weaker conjugate base or the weaker acids. So then let's look at the strength of acids and bases. And again, remember, we need to know this so that we can predict the direction of the reaction. A strong acid and base will react to give you a weak acid and a weak base. So first of all, you need to remember that the strong acids will ionize completely, which means that there will be no acid molecules left in there. For example, if you have something like hydrochloric acid, then there will be no HCl molecules left in the solution. Everything will be either hydronium ion or it will be chloride ion. So that means it's completely ionized. On the other hand, a weak acid like acetic acid will be in equilibrium, which means that at any given time you will have some acetate ions and you will also have some acetic acid molecules in there. So that's in equilibrium. So that's a weak acid. So in order to predict all these things, you'd have to have some sort of a theory as to what is a strong acid and what is going to be a weak acid. Okay, you will have to determine that yourself so that you can predict the direction of a reaction, and also so that you can predict whether something is a strong acid or a strong base. So there are a few conditions that are important for determining the strength of acids and bases: atomic size, polar bonds, which is due to electronegativity, and the number of oxygens, which leads to polarity. And this is something to do with electronegativity as well. Okay, but anyhow, these three are the things that we're going to be talking about. One thing I just need to remind you about acids is a strong acid is one in which the protons are in solution, okay? So the proton should remain in solution. That's how you know something is going to be a strong acid, which means that the acid is ionized, which is what I wrote over here also, is that strong acids will ionize completely. That's how it should be. So let's look at the atomic size first, all right? And so this has to do with bond strength. And the best way to look at the atomic size is the halo acids. In halo acids, you have start from something like hydrofluoric acid, then hydrochloric acid, hydrobromic acid, and then hydroiodic acid. Okay, and so looking at these acids over here, the only thing that is different is, of course, the size of the halogen. Hydrogen is the same, but fluorine is the smallest atom, whereas iodine is the largest atom over here. So the way the bonding works is, because this is covalent bonding, you had to have an overlap going on of electrons. And so if there is overlap going on of orbitals or electron orbitals, then the best overlap that you have is actually of hydrogen and fluorine, and that is because they are similar in size. Hydrogen and iodine are not similar in size. Iodine is way bigger than hydrogen. So the overlap here is not very good, which means that the bond strength is not very good. So if the bond strength is not very good, this hydrogen is not bound very well to iodide, which means it stays in solution. So if it stays in solution, that means HI is going to be the strongest acid. Generally, the thinking is that HF is going to be the strongest acid because we know of fluorine to be very high in electronegativity, and that is true, okay? But here we're actually looking at a different concept. We're looking at the bond strength. So because of very good overlap, HF is considered to be one of the weaker acids because the hydrogen is held very tightly to the fluorine. On the other hand, the hydrogen to iodide is not, okay? And so the strength of the acid is going to be HI strongest, and then HF is going to be the weakest one. That's how it works. So the same thing happens if you're comparing H2O with H2S. So hydrogen sulfide is going to be a stronger acid because sulfur is larger in atomic size, and so the bond strength is not very good. So which means that hydrogen sulfide is a stronger acid than water would be. And remember, water is actually amphoteric, okay? And so it's the same kind of principle anyway. So that is according to atomic size. Now let's look at polarity over here. So for example, when you're trying to compare HCl with H2S, okay, then HCl is going to be more acidic because the hydrogen chlorine bond is going to be more polar than hydrogen sulfide bond. Now it depends what you're comparing. If you're comparing things that are different in sizes, then you would use the bond strength. If you're trying to compare something that is different in polarity, then that is what you would use. You have to figure out what criteria you're going to use to compare. Okay, so in a question you will not be given the criteria. You're just supposed to figure that out yourself. So here in comparing HCl to HTS, you're looking at the polarity. When you're comparing H2O to H2S, you're looking at the size, okay, of the atom. So comparing HCl to HBRO, HClO and HBRO, the hydrobromous and the hypochlorous acid. Again, the HClO, the hypochlorous acid, is going to be stronger because the Cl is going to be more polar, okay? And so higher electronegativity, so it leads to more polarity. So the HO bond becomes more polar. So it's easier for this hydrogen to go away into solution and be hydronium ion. That's kind of how it works. The number of oxygen. Now remember, this has to do also with the polarity because oxygen is highly electronegative. So if you have more oxygen in there, that's going to lead to more polarity of the bonds. If there's more polarity, then hydrogen is more ionized. So for example, if you're trying to compare CH3OH, which is methanol, and compare acetic acid to it, the second one, the acetic acid, is going to be more acidic because you have two oxygen atoms, and because of the two oxygen atoms there is more polarity over here. So this HO bond over here, it's easy to break, so this hydrogen will get ionized. This hydrogen of the methanol, on the other hand, it can be ionized, yes, but not as readily as the one in acetic acid. Okay, so if you're comparing these two, then acetic acid is stronger. And then again, it's the same philosophy if you're using sulfuric acid and sulfurous acid. So sulfurous acid will be weaker because it has 3 oxygens only, whereas sulfuric acid is stronger because it has 4 oxygens, creating more polarity. So it's easier for these hydrogens to go away. Now for the Lewis acids and bases. These are completely different from your traditional Arrhenius acid and base and Bronsted-Lowry because Lewis acids are actually anything that can accept a lone pair of electron, whereas a Lewis base can donate a lone pair of electrons. So this has nothing to do with protons or hydroxides, nothing of that sort. So when you look at any compound and you're trying to figure out whether it is going to be a Lewis acid or base, you're looking for whether it is capable of accepting electrons or donating electrons. So the only way it can donate an electron pair is if it has an electron pair. So for example, a lone pair of electron, like in ammonia, where there is a lone pair of electron, or as in water, where it has two lone pair of electrons. An acid would then be capable of actually accepting electrons. So when you look at something like boron trifluoride, here if you look at boron, which has 3 electrons and 3 of them are bonded with fluorine, the total valence electrons on boron then are 6, which means it's capable of taking one more pair of electron. So if it's capable of taking one more, then obviously it's going to be a Lewis acid. So that's kind of what you're looking for. Okay, and Lewis acids can also be cations, as I said before, Fe2 plus, zinc 2 plus, and then another group mate of boron is aluminum. So AlCl3, that's also going to be a Lewis acid. So those kind of things would be acids, and bases would be anything that is electron rich. The way we write the reactions for Lewis acid base is exactly how it is shown here. The electron pair is donated from the base to the acid, but because it's donated over here, it really is shared, okay, over here. So a covalent bond is formed, okay, between the giver and the taker. All right, so it's not exactly like what would you call like an ionic bond. Okay, so you're not forming an ionic bond. These electrons are going to be shared between nitrogen and boron now. So this is kind of what it becomes. But the thing is that now that boron has more electrons, it now becomes negative and nitrogen becomes positive. And if you don't remember this little aspect, that's okay. Okay, no big deal right now. But I want you to remember that you will only form one compound as a result of this. And this is a salt, kind of, all right, because it is formed from an acid and a base. So we'll call it a salt. What you don't see over here is also water. And again, remember, the only time you would see water in an acid-base reaction is when you have an areneous acid and base. Okay, so here, Lewis acid-base reactions are very different, okay, when you look at them. One of the last things to talk about in acids and bases in this little introduction is how do you actually form acids and bases. Okay, if you look at any of the structure for acid, all acids are covalent compounds. Okay, and all covalent compounds are of course on the right hand side of the periodic table, all non-metals. Okay, whereas the bases, if you think about bases like sodium hydroxide, potassium hydroxide, they're all ionic compounds, almost all ionic compounds, and they also have a metal in them. Okay, that's why they're ionic. So which means that this says something a little bit about how these acids and bases are formed. So a lot of the acids are actually formed by taking any kind of a non-metallic oxide and dissolving it in water. So for example, sulfur trioxide will give us sulfuric acid, carbon dioxide will give us carbonic acid, nitrogen oxides will give us nitric acid. So you can take any of the non-metallic oxide and dissolve it in water to give you acid. That's how it works. And bases then are made from dissolving metal oxides. Okay, acids are non-metal oxides and bases are metal oxides. So take potassium oxide, dissolve that in water, it will give you potassium hydroxide. Magnesium oxide gives you magnesium hydroxide. And here is the equation for sodium hydroxide. Okay, so this is how it works for acids and bases. And again, remember that bases are coming from metals, so you have to have a metallic oxide. Amphoteric, on the other hand, are a little bit different because amphoteric can be acidic or it can be basic. And so think about the amphoteric substances that you know of, which really is just water for now. But some of the other amphoteric substances are aluminum oxide. So aluminum oxides will give us aluminum hydroxide and so on. And so these ones are amphoteric substances. So you will encounter a lot more of the acidic and the basic oxide questions than the amphoteric questions. So the key concepts to take away from this little presentation is that you should know the properties of acids and bases. You should definitely know what conjugate acids and bases are and how to write them, how to identify them. Learn about the strength of acids and bases. And remember, if something is a strong acid, it's going to be a weak base. Identify different types of acids and bases. Is it a Lewis acid? Is it a Bronsted-Lowry acid? Those kind of things. You should also be able to write simple acid-base equations and then identify acidic and basic oxides. And I said write simple acid-base equations. That also includes the Lewis acid-base equations.